Hello, I am back. And as promised, I have a short aside for you about the nature of spiral arms in galaxies. We know that all spiral galaxies have these spiral arms, but it isn't necessarily clear where the spirals come from or why they're there or why all galaxies with disks seem to have them. So let's take a brief minute and talk about this. It might be obvious that if you just start with two bars, let's say out to the side, that eventually it's going to wind up and look like a spiral. But that can't be the whole story. In other words, they can't be co-rotating, meaning the spiral arms can't be fully rotating with the stars. Let's first think about why that is the case. I've got a few links here to YouTube videos that I'm going to be showing you. They're not long. I will post them all, though, on the page with the videos. So here we go. Video number 1. So two galaxies here. On the left, we have a galaxy that starts off, they both start off pretty similar, actually. On the left, the spiral arms are going to be co-rotating with the galaxy. On the right, they're not. Watch what happens fairly quickly to the galaxy on the left. Doesn't take very many revolutions, 4 or 5, before the spiral arms, they don't cease to be, but they get wound up really tight. It's impossible to have a galaxy that's spun more than a few times and still have these fairly loose spiral arms. To give you a sense of scale of how long it takes, the sun takes about 250 million years to make one complete orbit of the center of the galaxy. So in a billion years, it's gone around 4 times. In the 5 billion years or so since the sun's been around, already it's made 20 complete loops around the center of the galaxy. So this happens fairly regularly over the even longer period of the galaxy's existence itself. If it were co-rotating, it would be very tightly wound, and it wouldn't look like this at all. Here's a simulation that's more like what we actually think is happening. So you're going to see in this simulation, the spiral arms, the location of the spiral arms themselves doesn't actually change. They're basically staying the same. Stars are orbiting the galaxy, and they're entering the spiral arms, and they're leaving the spiral arms. And so the constituencies of the spiral arms, or which stars are there, is changing all the time, but the location of the spiral arms within the galaxy itself isn't actually changing. And we think it's more like a density wave in this way, and not a wave of matter wave in that sense. And so this is what we actually think is going on in the Milky Way galaxy. This is similar to traffic. Traffic jams work in a similar way. Here is a fun video about how they recreated traffic jams in a controlled setting and just watch their behavior. It's kind of interesting. Take a look.
For the first time, Japanese researchers conducted a real-life experiment that shows how some traffic jams appear for no apparent reason. They placed 22 vehicles on a single track and asked the drivers to cruise round at a constant speed of 30 kilometers an hour. At first, traffic moved smoothly, but soon the distance between cars started to vary and vehicles clumped together at one point on the track.
Okay, I'm going to mute him now so I can actually talk about what's happening, but I want you to see what's happening with the traffic jam. I'm going to go back to here where it sort of starts. You can see this car is the culprit. But once it starts, it sort of is a self-propagating thing. And you can see, so cars enter the slowdown and they leave the slowdown, but the slowdown itself isn't traveling in the same direction of the car. In fact, it's traveling backwards. Right? As you can see, these cars actually come to a stop, and the jam itself moves backwards around the track. And we don't think that's exactly happening in galaxies, because stars don't actually stop when they reach the spiral arms. But it's possible that these spiral arms could be rotating in the direction of the motion of the stars. They could be stationary, or they could even be moving backwards. All of those are possibilities for what these spiral arms are. We get some hints that this is actually happening in real galaxies themselves. You can see on this side, the stars are moving in this direction in this particular galaxy counterclockwise. And you can see on the leading edge, as stars move in, these gas and dust clouds are sort of piling up. And this is where we get star formation happening, where the density increases, and we get these gas clouds piling up and increasing in density. And then in the trailing edge, we see these bright stars that won't even make a full half orbit around the galaxy the massive ones before they actually go supernova and die. So you can sort of see this happening in real time in this particular galaxy itself. Okay, moving on now to the Hubble law. So Edwin Hubble would have been famous if all he had done was solve the Curtis-Shapley debate by measuring the distances to galaxies using Cepheid variables. But he took it a step further and discovered one of the most amazing laws in all of the universe, which now bears his name, the Hubble law. So he, again, was measuring the distances to nearby galaxies using Cepheid variables, and he was also taking spectra of these galaxies and measuring their relative velocity with us. And he found some remarkable relationship between distance and velocity we'll talk about for a second. But I want to talk about the remarkable thing about the velocities first, because this was known even before Hubble's time. Almost every single galaxy that we see in the universe, with a few notable exceptions that are all very close by, have a positive radial velocity, are moving away from us. Let's look at what that looks like. So how do we measure the radial velocity of a galaxy? You might remember from our study on light, we take a spectrum of a galaxy, we take a spectrum of another galaxy, and we notice some features that are similar and that you can identify from both of these galaxies. For instance, these two may be absorption lines. And you can measure the radial velocity of an object if you can see how far this has been redshifted or blue shifted. And when you do this for stars, you find that there's a random distribution of velocities. Some of them are moving towards us and have negative radial velocities. Some of them are blue shifted. Some of them are moving away from us and are red shifted and have positive radial velocities, but there's no correlation between anything. It's just a random mix. That's not the case for galaxies at all. Almost all of them, with very few exceptions, are moving away from us. And that means they're almost all redshifted, they're virtually all redshifted, which is weird. It goes more than that. So here I have a fun animation where we can measure the distances and radial velocities of galaxies fairly quickly. Let me pull this up. Here it is. Make this a little bigger. No, oh, there we go. Okay, so I've got my telescope here, which don't actually stick out of domes, but that's okay. And I can click on these galaxies. Here's M106, and I can get very easily, in this particular case, the velocity and the distance. So let's go ahead. We're going to plot. We want velocity on the y-axis and distance on the x-axis. So let's just plot those numbers. There it is. There's M106. A nice, beautiful spiral galaxy. Here's M108, another spiral galaxy. A little further away, moving away from us a little bit faster. Pretty fast. Look at these numbers. 695 kilometers per second. That's really fast. Here's M64. Here's M66. Here's M82. It's pretty close by. M98. And something interesting happens here. You'll notice that for all these spiral galaxies, a general pattern develops where the further away the galaxy is, the faster it's moving away from us as we add these data points. That's very weird. Nothing like this was expected. Well, it works for the spiral galaxies. How about for the elliptical galaxies? Let's click on those guys. Here's M87, a nice elliptical galaxy, one of the bigger ones in the nearby universe, 18 megaparsecs away, 1282 kilometers per second. Bam, right on the line. How about this elliptical galaxy? How about this? Doesn't matter what kind of galaxy you look at, they all obey this particular law. Distance from the Earth in millions of parsecs and velocity away from us in kilometers per second. And this is only a nearby region, but we get a much better, tighter view when we use modern data and go out much further than this. This is a well-established relationship between distance and velocity. So all galaxies are moving away from us. And not only that, the farther they are away from us, the faster they're moving away from us. Let's take a look at some more examples. Oops, that's not what I wanted to share. That's what I wanted to share. Here's an example of 5 different galaxies. at very different distances. You can tell we're using actually the method of standard rods. There is a reason for us to believe that all of these galaxies have about the same intrinsic size. Oops. So we know that this galaxy is the closest to us because it's the biggest, and as you go further away, the galaxies get smaller and smaller. And over here on the right, we're looking at these radial velocities by looking at the redshift of these two particular lines, H and K. Already in this galaxy, they're at 1,200 kilometers per second. And you can see the lines go further and further to the right. The red sort of shows you, the red arrow shows you where those two lines are in each of these subsequent spectra. And these have extraordinarily large radial velocities, 1,200, 15,000 kilometers per second, 22,000 kilometers per second, 39, 61,000 kilometers per second, which is very fast, right? What is the radius of the Earth? Something like 6,400 kilometers. That's 10 times the radius of the Earth, or 5 diameters of the Earth. In 1 second, this galaxy is moving away from us that fast. And all galaxies that have this distance are moving away from us that fast. What could possibly get these galaxies, whole galaxies, moving that fast? And think about this, 61,000 kilometers per second. 60,000 kilometers per second. That is a significant fraction of the speed of light. What is the fraction of the speed of light? Let's quickly take a look and do that problem together. Oh, look, my way forward's back. So the star, the galaxy, has a velocity of 60,000 kilometers per second. Do you remember what the speed of light is in kilometers per second? You can look it up, but it is 3 times 10 to the 5 kilometers per second, or 300,000 kilometers per second. Remember, it's 3 times 10 to the 8 meters per second, 3 times 10 to the 5 kilometers per second. So fraction of the speed of light, that's just V over C. That's 60,000 kilometers per second divided by 300,000 kilometers per second. What do you get? 0.2. 20% the speed of light. This galaxy at the bottom of this screen, the previous slide, is moving away from us at 20% the speed of light. What on earth could get that galaxy moving that fast? And all galaxies at that distance moving that fast. Crazy to think about. Okay, we've answered that question. When you do a more modern view of what this looks like, this is the Hubble flow. This is the, better version of the graph that I showed before. A beautifully tight relationship between how far a galaxy is away from us and how fast it's moving away from us. This is very weird, but we will think more about this equation, think more about this relationship, and develop an equation that's going to fit this line in the next video. So stay tuned.